Hi, this is Track A, Maths and Statistics. Today we are looking at Part 2, Linear Algebra. Today we are going to discuss about ranking, decomposition, and the math behind low ranking adaptation. This is week 2 and hence part 2 of the Principal AI program. One module and one destination that we are looking at is, hey, why fine tuning a model is uh, is very costly, and how can we reduce it for much cheaper. It will take around 1.5 hours, and we require it as a prerequisite that you go through the week 1, which is part 1 of this track A, where we learn about vectors, the dot product, the cosine similarity versus Euclidean distance. Then we looked at matrix multiplication. We looked at the basis and the independence of various elements. How will you know that you have completed successfully this part? You will be able to explain to a CFO saying that, hey, why fine tuning a $7 billion model, 7 billion parameter model, went from renting 8 GPUs per week or for a week to 1 GPU for one afternoon. Yeah, and if you can reason it out on a napkin, all the best. We are having a lot of stuff to cover. We'll start with ranking. We in ranking we our ranks in calculating the matrix ranks. We are going to understand how much independent information is actually available in a matrix, if there are duplicates between rows and so on. Linear transformations, will read a matrix as a machine that reshapes in space. We are going to look at eigenvalues and eigenvectors, while linear transformations move the vectors around. Some do not, and those are eigenvectors, and we'll look at how to compute them by hand. We'll look at singular value decomposition, which is SVD. We will explain the universal decomposition technique and why applied AI reaches for it. Then we are going to look at low rank approximation. We are going to reason quantitatively about the compression and what quality trade-offs exist there. Then we are going to look at PCA, which is principal component analysis, and matrix factorization separately as topics, but they are one idea. Then we are going to compare sparse versus dense matrix compositions, and we will know which one of our product's data quality actually it is. Finally, we'll look at low rank adaptation, and we'll do the mathematics behind it, and we will derive them from the first principles, and we'll defend a rank R as a product decision, not engineering decision. So while part 1 gave us a lot, part 2 opens up that transformation layer. How are we transforming the data? Yeah, every matrix, a data set, a network layer, or a user item rating table that we look at breaks that into a smaller number of independent directions with strengths. The strength of those is what is the individual ranks that we will look at. Yeah, all of them have far fewer meaningful directions than their size suggests. Yeah, so be enthusiastic. If you haven't already done part 1, go and come back, because it has a lot of dependency on it. Let's first understand matrix rank. Yeah, matrix rank explains how much information is actually hidden in there in the matrix, and it also helps us understand the number of genuinely independent directions in a matrix, and it doesn't matter how big the size it is. So let's understand what a rank is. Yeah, a rank of a matrix is typically the number of independent rows, equivalently columns as well. It is the dimension of the space the matrix's column can actually reach. So if you understand matrices, they are rows and columns of data, and with them they carry a lot of vectors in individual dimensions, and the whole size of the matrix, which contains rows and columns, is what is stored, but not all of that is actual data. and in that very few rows and columns will have unique data, rest all are duplicate, redundant, noisy data. If we remove them, whatever remains as the number of rows or columns is what the rank is. Yeah, this distinction is the whole module. Yeah, we need to understand how unique the data lies so that we reduce the number of rows and columns. Yeah, and that techniques that we'll apply here are compression, PCA. It is applied through recommenders, uh, movie recommendation in Netflix. You're going to look at low rank adaptation, which is used to reduce the model size for fine tuning and so on, and we will exploit that gap between a matrix size and its rank. So imagine there is a 2 by 2 matrix and you want to calculate the rank. Yeah, all we need to do is find the determinant. So imagine if there is a matrix like A, which is 1 2 2 comma 4. It has two rows. To calculate the determinant, what we do is we multiply 1 and 4, subtract these two, multiplication of these two. So it is 1 into 4 minus 2 into 2, which is 0. Yeah, the determinant is 0 and hence rank 1. If you want to calculate the rank of P, so here it's very clear, hey, B can be derived from A by multiplying with 2, but here it cannot happen, and hence even the determinant is not equal to 0. Yeah, it it just looks at these four numbers and it holds one direction and one scale factor. Yeah, the determinant 0 is the two-dimensional way of saying here the row our ranking has collapsed. Instead of 2 as a rank, it has now become 1, because this is a duplicate and we can derive from this, so the rank is just 1. Here the rank is 2. We have already seen in week 1 that if you had the price in INR, you could multiply by a certain factor to arrive at price in USD. The same applies for rank as well. Yeah, so rank is telling us what is that duplication, noise, redundancy, or a waste. Yeah, and that's the formal name given for that opportunity. And the words that engineers are going to use will look something like this. They'll say, hey, it is a full rank matrix. That means that there is no redundancy at all. Yeah, rank will mean the minimum number of rows and columns. Every direction has its own place there. They'll say, hey, there is rank deficiency, or there is low rank, as in fewer independent directions than the total dimensions. So this is where you can apply all the dimension decomposition techniques to reduce, or PCAs, to reduce the number of rows and columns. And effective rank, the honest version. Yeah, the real matrices are rarely exact low rank. They are low rank plus some noise. Yeah, exact duplicates we will not find. We will find some duplicate plus some noise at the bottom. So effective rank asks how many directions carry meaningful signal. So that unique, or top k, needs to be identified as the unique directions, and that will give us the rank. Yeah. So imagine there is a 1536 dimensional embedding space. This is what we use for embedding text into the vector spaces. And if you're asking, hey, how much of this embedding space is our data actually using, because many of them will be zeros or so, we need to look at each of them. For example, if you use a corpus of purely support tickets, it will not use these many dimensions. It might use 256, 512 dimensions, are closer to 400 to 500. The rest of the dimensions are pure cost, they are storage, the index size increases, the query latency increases because you have a larger index size now to search and get you the data. Bandwidth increases because we are doing a lot of multiplications and so on, with no quality attached. As in, the quality does not improve as such. Though we are using 1536, hardly 400 is the actual data. Yeah, rank turns that vague hunch of we are overpaying into a measurable quantity. Now you should be able to say, instead of using 1536 dimensions, can I reduce the dimensions to only keep the ones that are giving us value? And in matrix multiplication, this is how it works. So for example, there is a duplicate row. So this row is a duplicate of the first row. If you notice, 1.2 minus 4 point minus 0.7, 0.3, 2.1, 0.5, and so on. So these two are duplicate rows. The training on this particular data is not going to help us in that dimension. These two vectors are rows again are duplicate, exact duplicates. Sometimes they might not be exact duplicates, they might have some commonality or some noise in between them. Yeah. What rank which will uniquely tell us is, hey, if are all the vectors lying on one line, yeah, then it only means if it is rank 1, yes, they will all lie in a line. If it is rank 2, they will all lie on a particular plane. If it is rank 3, they will all lie in a particular three-dimensional space bounded by three planes, or four planes, sorry, in that case. So what we effectively are saying that, hey, you need not have 1536 dimensions. You can always use an effective rank which is lower than 1536 dimensions, and it makes that compression possible. You reduce all the dimensionalities into this compressible space, thus saving your space, your query latencies are reduced, lower storages, and everything. Yeah. And most information lives in that lower dimensional space and not this higher dimensional space. So how do we do this as a process? We first identify how many independent directions exist. From that, we take on what are those dimensions which actually make sense. Then we apply a removal of those dead dimensions. We remove those redundant dimensions. We only keep certain required top k dimensions, and this helps us in lowering the cost through lower storage, less compute, lower latency, and it improves user experience as well, because now the speed at which text can be found and everything is found increases. This brings us to linear transformation. We learned in part 1 that we saw matrix as an engine and are a machine that helps us reshape the space, and today we're going to look at four such transformations that are possible because of that machine or matrix. And we are also going to look at why when we do certain operations they cannot be undone. And we need to understand this, that oh, whenever these shapes or the vectors undergo transformations, many a times, if not almost all the times, the straight lines will stay straight, they will not bend, grid lines will remain parallel and evenly spaced, nothing curves. Yeah. And the origin stays put. Yeah. If the origin is 0 comma 0 comma 0 comma 0 so on till 1536 dimensions, it will still be the origin. There will be no translation or no movement of origin. Yeah. What we are going to look at is how do we take individual vectors and how can we rotate, scale, shear, project, or flip them. That's what we are going to look at. And that's what we learned in part 1 as well. We called matrix a machine. Yeah, this concept opens up that machine, opens up that transformation stuff, and it shows us how do we transform in all of these layers. Yeah. And the four transformations that we are going to look at are scaling, rotation, shear, and projection. In scaling, what we do is we increase the size of the matrix or vectors. If if a matrix was 1001, we could multiply it by 2 and change the scale of the vector. Yeah. The origin would still be referenced on 0 0, only the change. Rotation, using 0 minus 1 1 0, you can rotate the shape of the matrix or the vectors. In this context also, the origin remains at 0 0 0. The lines remain straight, they do not bend. Shear, it slants the shape horizontally or vertically, and if it was a square earlier, it could become a parallelogram. Projections, we drop one dimension to project a point in space. If it was two-dimensional space, like here we have x and y, we project the point onto the x-axis and it becomes a singular dimension. Now if you notice, in scaling, rotation and shear, all these three, we were able to rotate, scale or shear the dimensions. Their origin was still the same and the vector is still the same, but in projection the dimension collapsed. If it was a two-dimensional uh, vector, now it became one-dimensional in nature. It reduced dimensionality by one. Yeah, and that's the loss of information that we can't undo. And rank loss is information loss. That's what we were trying to say. Some transformations means that while the rank is reduced, it becomes non-invertible in nature. Yeah, the projection matrix has rank 1. It squashed a two-dimensional space into a one-dimensional line, and the y coordinate is gone forever. Now we have no way of finding out what the original score was or the original vector was. Yeah, so there is no inverse matrix that exists because the rank was dropped. Yeah, reversibility is not a property of the numbers in the matrix, it is a property of its rank. Okay, and whenever rank falls, something has been thrown away. We need to always remember this. If a three rank matrix became a two rank matrix, something was dropped. Yeah, and that important information is lost forever now, and we cannot bring it back. But if it is a um, but if it is a two rank matrix that became two rank matrix only, we need to find out what transformation took place, and if we inverse that, we'll be able to bring back that original matrix. And that's the deliberate rank trades that we do in system production systems. For example, quantization. In quantization, what happens is you reduce the numerical precision of weights. If you have a float 32 precision model with 70 billion parameters, and if you reduce it to a maybe 4-bit or a 8-bit, which is 8-bit floating point, um, 70 billion parameter, the model size will reduce. But what will happen is you will make it irreversible. Yeah, you can't bring back the precision again, and with that the quality also would reduce. In dimensionality reduction, if you can wait for a couple of minutes, we'll see this in point 6. But what we are saying is, once the directions are discarded, for example 1536 dimensions, you have a matrix, uh, now you reduce it to 512, you lost some directions, you have discarded them on purpose. Now you cannot bring that back, and hence the non invertibleness. Yeah, pooling of layers. In convolutional neural networks, they have something called pooling of layers. Many activations, they are collapsed into fewer ones. That's done through pooling layers. They pool multiple activations into fewer ones, and there also we lose a lot of dimensions, and hence the non-irreversibleness or irreversibleness. Um Embedding truncation. We just spoke about 1536 to 512 if you reduce, yeah, in vector databases. Aggregation in analytics. Suppose every day you add certain numbers and voices and keep only the total. Now on day 30th, your manager or some person using that analytics asks, hey, what were the individual components of these sums? We wouldn't know because we have never stored them. Yeah, so a daily count cannot be unsummed back into individual events. Yeah, each is a choice to trade information for cost. The skill is in choosing knowingly. Now let's understand what are eigenvalues and eigenvectors. Yeah, it is eigen. I do feel strange the first time I learned the pronunciation of this. Yeah, we know that whenever vectors undergo transformation, they move in shape from the position. While the origin still remains the same, they are still straight lines. They might move in direction a little bit and so on. So when this happens, a few of them they still point in the same direction. These are called eigenvectors, and their distance is measured in eigenvalues. Yeah. So which directions survive a transformation unturned? These are eigenvectors for us, and eigenvectors can typically be represented by AV, yeah, which is the result after transformation, and they can be represented by lambda v, where lambda tells us, hey, there is a single value which is the eigenvalue, and v being the actual vector, yeah, eigenvector. So if av can remain or can be represented by lambda multiplied by v, then these becomes our the v becomes our eigenvector, yeah. So eigenvalue is a stretch factor. If it is greater than, when we know how much it can stretch, how long it can go, how lengthy it can become. But if the lambda value is between 0 and 1, we know that the value is shrinking in nature. But if it is less than 0, it is a reverse, as in it turns 180 degrees or so, and then stretches in the negative directions. Yeah, so eigenvectors are the natural axis along which the system acts by simple scaling. That's what we are trying to say. And this is a simple good example where if we have a matrix like 2 1 1 2 and a vector is 1 comma 1, we can represent this as ab is equal to lambda b, where lambda becomes 3 for us. If the vector is 1 minus 1, then lambda will be 1 for us. Yeah, we can determine that. And we can also uh, find out the value of lambda if we don't know the answer by doing a minus lambda is determinant is equal to 0. Yeah, so in that case we do 2 minus since we know the value of a and I, we can take the determinant of a, which is 2 to the 4 minus 1, which becomes 3 in that case. So 2 minus lambda whole square minus 1 is equal to 0, you know, and we can then get the value of lambda is equal to 3 and 1. Yeah, in this case what has happened is 1 comma 1 is stretched by 3, 1 minus 1 is left untouched. Yeah, that's what is happening here. So eigenvectors are the transformations natural axis, as in they don't move in direction. Yeah, the direction gets amplified but it doesn't move. It dominates the behavior of the system and of anything you build on top of it. So lambda near 0 means the direction gets crushed, as in it's directionally not helping much along in that axis. So signal along it is being erased with every application. The more the transformation happens there, the lambda becomes closer and closer to 0. Yeah, and whenever engineers say a dominant mode, spectral graph, or principal directions, they are all saying that, hey, look at the point where these large eigenvalues exist. So what this helps us to understand is, if there is q lambda q inverse, then we know that q is a matrix of eigenvectors. We can find out a using this formula, you know, where lambda is the diagonal matrix of eigenvalues. We need to read this from the right to left, because the calculations need to happen in this direction. Yeah. Um, decomposition is not general enough. It requires a square matrix, yeah, because without that we will not be able to do the inverse and all. Yeah, uh, our data matrices are almost never square. They are they are rectangular in shape, if I have to say so. Yeah, 1,000 documents by 1,536 dimensions in a rectangle space, you know, that's a rectangle. So that limitation is exactly what next concept is all about. Yeah, you know, where do these eigenvalues and vectors show up? In PageRank, for example, PageRank algorithm of Google. Yeah, the web's ranking was the dominant eigenvector of the link matrix. Principal component analysis, where we identify the eigenvectors of the covariance matrix. Spectral clustering and stability analysis, grouping and long run behavior, both read off the spectrum. So both read off the spectrum, sorry. So what we are trying to understand in all this is which are those eigenvectors that do not change in shape and are the dominant vectors in the matrix. This brings us to singular value decomposition, which is solving the problem we just said here. Here we said, hey, there are certain limitations that are posed by eigen decomposition into eigenvector and eigenscalar or value. Yeah, which was that? It was a square matrix. Now, singular value decomposition solves for that. Here, matrix can be of any shape, and still we will be able to decompose. So here a formula is still similar. There we looked A is equal to Q lambda Q inverse. We are looking at here it as U sigma and V transpose. V is that right singular vectors that we are gonna look at. Then we have sigma, which is the singular value summations. Singular this is more like an identity matrix, but instead of ones we have a lot of singular values like sigma 1, sigma 2, sigma 3 and all. And then finally we have u, which is a left singular vectors. And in singular value decomposition, what happens is we take the original matrix, we rotate it using the V transform, and then we stretch it. And stretching, we identify which are those sigma values which make the biggest um, difference. We use them sigma 1, sigma 2 until sigma n, the smallest one, because the larger the bandwidth, the higher the water flows, and the larger the explanation of the matrix by those dimensions. Yeah, then we rotate back uh, the matrix that comes out of this stretch phase, and that's where we get the final shape. So why UV are the boring but beautiful part? In orthogonal matrix, though it has columns that are mutually perpendicular and of unit length, we observe that three properties make them beloved. One, the inverse is free. Q transform into Q is equal to I. So we know that if you pass on Q, which is I by Q, which is Q inverse, then Q inverse is equal to Q transform. Yeah, undoing it costs a transpose, nothing more. Yeah, lengths and angles are preserved. We are only doing pure rotation and reflection. There is no distortion or information loss that is happening. So rank is always untouched. Yeah, and it's numerically stable as well. Errors don't compound when you chain them. We are only doing three actions in sequence here. There is no compounding nature that takes place. So all the interesting behavior is pushed into the diagonal sigma. We'll look at it this. We look at how the diagonal looks like with the sigma values, and everything around it is a distortion free rotation. So while the length everything changes a little, it doesn't get distorted, and this is why decompositions are built this way. Yeah, the rank a will still remain as the number of non-singular values. So this is where that sigma matrix exists, and we can plot that on a log scale. Yeah, and look for the elbow where the most optimal number of dimensions can be found as well. Yeah, let's so sorry. So singular value decomposition is that workhorse. Even today, a lot of computers use singular value decomposition because it's easier to calculate the top n number of singular values that can be decomposed to identify the right values. Yeah. This brings us to low rank approximation. Yeah. So SVD only sorted the information by sigmas. We looked at here it's sorting the largest sigma values from top to bottom. And now low rank approximation helps us retain the top k and throw away the rest. So how does that happen? The formula still remains the same: u underscore k sigma underscore k v underscore k transform. So the whole formula remains the same, but we take the top k and drop the others. So among all possible rank k matrices, the truncated SVD, which is singular value decomposition A underscore, is the closest one to A, because only fewer elements have been dropped. No cleverer rank A approximation exists till today. So this is one of the best decomposition matrices that we see, which is able to reduce the number of dimensions without loss in the values. So whenever an engineer says we are using SVD, PCA, or low rank, they are standing on a theorem, not on a hunch, because this has been proved through Eckhart Young, and that should raise your confidence in the approach and sharpen your questions about K. Yeah, and you should ask how many K have been retained. That's all we need to know about. How it was chosen, that's what we would need to know. Yeah, here is a very good example that we could look at. Imagine there is an image which is 512 by 512. Yeah, if you multiply these two, you will get 262k 144 individual points in a matrix. And this image is very good. Storage requires so many floating point numbers. If it is color, then it requires into 3. That much storage space is required. Now imagine we decompose this into this. Yeah, you have a U matrix, you have a sigma matrix, you have a V transpose, and in this sigma we have sigma 1, sigma 2, sigma 3, and so on till sigma n. Yeah, because this is m by m, this is m by n, and this is n by n. Okay, we looked at the dimensions where here m by m, m by n, and n by n, and that's how we get the A matrix, which is m by n. Okay, so now if we look at these m by n, this is m rows and n columns. We need to just look at these n sigma values and say, hey, keep only the largest singular values top k and discard the rest, and that is until sigma r. Okay, remember this, because we are gonna look at more r in upcoming this. So we can reconstruct this image by using minimal sigmas and not the all, and that's what it's helping us reduce the storage costs, reduce the computation costs in real time as well. Yeah, and as a as an individual or a user, our naked eye can't perceive the difference between these two images. They at least look the same to me. Yeah, and one unique thing that we need to notice is the elbow method. When we put all the sigmas, sigma 1 to sigma k or sigma n, at k we can say, hey, these are the most important k components that help us retain the most of the information, while the rest of them do not really help, so we can drop this. So for each of these k's we can retain only those. For example, if you retain 50 of those top ones, the number falls to 51,250. That is almost like 20% of the storage. 80% reduction has happened by reducing the number of dimensions. And we know that if you put a graph on storage used versus reconstructive quality or reconstruction quality, we see that after 20% there is hardly an improvement on the quality, even though the storage increases. So we can cut it off here and say that, hey, enough is enough. For 20% I'm getting the close to one the equivalent quality of 100% as well. Yeah, even though the storage increases, the quality does not. So let me cut here and take these many elements only, and that's why compression becomes a choice about k. And remember that it's not a free lunch. You need to calculate the right values for it to come up. So we need to ensure that m plus n plus 1 is always less than m dot n. Yeah, for a 2 by 512 by 512 image, break even is somewhere around 256. Instead of 512, it comes around 256k. Yeah, and every AI cost decision has this shape: a dial with a break even point and a quality curve that has to be measured rather than assumed. So quality also needs quality So the quality always needs to be considered against the storage costs. Yeah. This brings us to dimensionality reduction and PCA. You suspect most of your 1536 embedding dimensions are near redundant for your corpus, and this technique, which is reduction, dimensionality reduction, or PCA, helps you weigh that truth in that. Okay, so it happens in 4 steps. With PCA, what happens is you take all the data, you center it around 0. Yeah, you subtract the mean of each column, and then you subtract it, you find the maximum variance that exists, which is sigma square, and then we find orthogonality and take the second dimension and go on from there, and we retain only the top k that we need for understanding the complete matrix from that few minimal dimensions. So that's how PCA becomes the SVD on centered data. Singular value decomposition is also doing the same. PCA does it on centered data. When centered data we mean, it takes the mean of the data and subtracts the rest from that. Yeah. So what are the principal components for whom we are doing analysis? Nothing but the right singular vectors. That's all. And the variance is explained by that sigma square. That's all we are saying. So one decomposition, two vocabularies. What are those two vocabularies? One, principal components, and the singular vectors that we are looking at. Yeah, knowing they are the same saves you from a whole class of confused meetings. True. And explain variance of each component is done by sigma 1 square by sigma j square. Total sigmas compute by individual sigmas squares. Yeah. So the top 50 components capture 90% of 92% of the variance. So this is what we should be able to understand and convey as a meaning. Yeah. If um, if not all of the components explain the variance, if top k, which is in this case top 50, can explain the variance of 92% of that variance, it is a very good representation. Maybe we should stick to top 50 itself. So it explains actually how much of the spread in my data survives the cut. So ensure you do not cut it so much also that you're not able to really explain the whole of the image or the data, text data. We need to be very prudent about how much we do the cut on. Yeah. And this is where the three things that come as caveats we need to be very careful about. Variance is not usefulness. Okay, if there is too much variance, it does not mean that it is the most useful thing. What we need to understand is that a low variance direction can be exactly the one that separates your two classes. Yeah, we need to gate dimension the cuts on retrieval metrics and not on the explained variance alone. Yeah, principal component analysis is linear. Yeah, it means that so it means that you do PC1, PC2, PC3, and so on, and the meaning in embedding space is not always. UMAP TSNA handle a curved structure better for visualization, but they do not preserve distances honestly. So never use them for retrieval. We cannot use it for retrieval. Only for embedding space, we could use a little, but not beyond that. And Matryoshka embedding actually solved that problem recently. And this is being used as default for text embeddings recently, because they help us reduce the dimensions without loss in quality. Yeah, they do not do overfitting, they do not do underfitting, they are very close to the right fitting. Yeah. And in 2026, if an engineer says or proposes Matryoshka embedding over PCA, we should be able to say, hey, thank you for doing that. And that brings us to a very interesting part of this session, which is matrix factorization. In part 1 of week 1, we looked at user into item gave us the predicted affinity between the users and the items, which was in that case movies. But one question was left open, that was, hey, where do these vectors come from? And that's what we are going to look at today. um, let's take with an example. Imagine there are users, and we transform is the number of items that we have. Typically what we get is users by items matrix. Yeah, we're going to look at in the next slide on how that looks like. But typically in a database where we have lots of users and lots of movies, we have their ratings against each of the movie. And many times there is a lot of open spaces because not all the users have watched the hundreds of thousands of movies. So what we could do is, in factorization, we could split this into users into k and k into items. So users becomes users matrix becomes users into k, where users is a matrix, and sorry, users is the number of counts of users, and k is the dimensions that helps us preserve some aspect of the users affinity towards movies. Whereas here we have k as the same number, that is users affinity towards movies, certain movies, into the total number of items. Okay, so imagine there were users, which could be 1 million 1 million users, and there are 100,000 movies, for example. So we know that user 1 has watched movie 1, movie 3, movie J, and so on. He would not have watched all the movies. So wherever he has not watched, we typically have no information. Yeah, there is a rating that is missing in this case. And typically for such large sparse data matrices, what we typically do is we do factorization, where we split them into user matrix and into the movie matrix. And k is the latent factors in space. It could be identity matrix, it could be anything else. And what we typically need to identify between these two is k is a minimum value of m by n, yeah, so that we don't lose value here. Okay, and from this, ui becomes the first row, vj becomes the uh, first row, or in this case it could be column, because here you are looking at it as column, but in this case it becomes a row. Okay, and dot product of these two will typically give us that complete matrix. uh, what happens by doing this factorization is, rest of the um, way, gaps that you find here are actually filled in by these. So we are making this matrix a little denser in if you separate them out. Okay, so imagine there are 100 billion ratings that were supposed to be given, which is 1 million users by 100k movies, which gives us 100 billion ratings. Okay, users by movies, extremely sparse data. What we can reduce it to by doing factorization is 55 million parameters we can reduce it to after factorization, by applying a k value of 50. So this becomes 1 million into 50, which is 50 million. And we have 100k into 1 million into 50, which becomes 50 million. And this is 100k into 50, which is 5 million. Okay, if you sum those 50 million plus 5 million, you get those 55 million parameters. Okay, and if you compare this 55 million parameters to the 100 billion initial ratings, it is a 1800x drop. Yeah, it is smaller, much smaller, when you consider these two parameters. Yeah, and how do you name those k dimensions? We do not. Yeah, that's the part one's misconception. We are trying to say that, hey, the same rule governs embedding dimensions as well. Only directions and regions carry meaning, never the individual coordinates. So we don't know whether each of those dimensions has a meaning. We know for sure that there are so many dimensions, but we don't know what those dimensions carry as a meaning. Yeah, uh, can you show me what dimension 47 means? No, we do not have that answer. Yeah, and that's why interpretability is its own research field. And the Netflix prize made this very famous. You can read on this more. I'm gonna skip this, but what actually happened are worth knowing is that in production, this fit with alternative least squares or gradient boost machines that were used rather than the uh, SVD, because R is mostly missing values, not zeros. Okay, a missing reading means unknown or not disliked. Okay, the treating of the two as the same corrupts the result. So we should not corrupt them. We should keep it separate. Try to predict what could be a value in that space. Yeah, the mental model is identical. Only the fitting procedure changes. And this brings us to that important concept of dense versus sparse matrices. This will sound like a trivia, but you know what sparse is, you know what is dense, okay? But it really drives the infrastructure choices, okay? And it explains why cosine similarity means anything at all. Okay, that's what we are going to look at. Imagine sparse, you have lot of space, and most of them are zeros, and only few of those values are done. Yeah, one hot vector encoding is also following the same. Term frequency or inverse document frequency also follows this, where you try to reduce the number of um, um, values for a given vector if they are very rare in the document. Yeah, best match 25 also follows the same concept, where very few vector components have numbers, rest all are zeros. Okay, user item matrix is also sparse. So all these are sparse representations where very few numbers have values, rest all zero. So mostly zeros is the characteristics. They are high dimensional in nature because they are pretty large. They are fast and efficient because you only have to identify these numbers, and they provide exact matches. You know for sure that user 2 has watched item 1, and hence the score is 4. Now with dense representations, where we have seen that all the numbers are populated. Yeah, word to word embeddings, we saw that, yeah, for each of the 1536 dimensions, whatever it is, in embeddings, all those dimensions are generated, values are there. Yeah, there are hidden states in transformer representations. User item embeddings, we saw that when you split them as a user versus item, we get all the values. Yeah, the characteristics are little different from here. So here mostly zeros, here there is no zeros at all. This is high dimension, but this is low dimension because compactness is of the need here. It's fast and efficient. Here it captures meaning, so relatively slower compared to your sparse representation. Here it exact matches. Here it's more on similarity or semantic matching. Okay, and that's why sparse versus dense, it's a little difference. You want precise matches, you go to sparse. You want semantic matches, you go with dense representations. Yeah, these are great for meaning and context. These are great for keyword and filtering and so on, where exact match is the need. So this is what we had learned in part one's track E, also on the word to vec paper that was published in 2013. We were saying that, hey, the text was represented sparsely in a 50,000 dimensional one hot and vector per word, all zeros except a single one. Yeah, in that representation, every pair of distinct word was orthogonal. So king and queen were exactly unrelated. So this would mean that king and carburetor could be matched as well. Yeah, similarity was not merely hard to compute, it was mathematically absent. Okay, word to vex contribution was the move to dense vectors of roughly 3300 numbers, where similarity became measurable. Yeah, we saw how cosine distance, yeah, dense siblings are the reason cosine similarity means anything at all, because this was used for um, understanding the similarity between two vectors in space. And in all of 2026 vocabulary that we are talking, these are the additional words that you'll keep hearing. One is mixture of experts. uh, we don't say, hey, choose this versus this. What we are going to look at is a combination of both. Okay, so when a vendor quotes activators versus total parameters, what they mean is only few parameters being used versus the total size of the actual parameters. Only few are being activated or multiplied with to get the actual result, not all total tokens. Sparse and efficient attention, we don't compute all the token pairs. Yeah, we saw that attention is not all the big O notation of O n square, and compute a structured subset instead is what we are saying. We are saying don't compute everything. Hybrid retrieval, we saw best match 25 keyword matching, which is sparse combined with embeddings, which are dense in nature. So how do you combine that? Yeah. So in 2026, we are looking at like sparse is usually a cost efficient strategy because only few multiplications happen, because there are only few numbers to multiply. Dense is usually a semantic quality search because there is closeness between the text, not exact but semantically a matching text. So how does this play in 2026? It's a combination of both. You use both. If you're looking for exact match, use BM25. If you're looking for semantic meaning level matching, use embeddings which are based out of dense embeddings. Yeah, and that gives you the best search results with high precision and high recall. And that brings us to low rank adaptation mathematics. This whole module A2 or track A part 2 exists because of this low rank adaptation mathematics. Okay, every concept that we have learned so far actually converges here. We looked at rank, we looked at decomposition, and the idea that updates are smaller than they look is what we are going to explore here. Okay, so the foundation models that we are looking at are typically in billions of parameters, and even if we take a decent sized 7 billion parameter model, and if it is a 16 floating point precision that it has, we are looking at anywhere between the model's weights alone being of 14 GB. Yeah, if there are gradients that we are trying to fine tune, then it adds every uh, bit to bit equivalent, there will be 14 GB this. If you're looking at optimizer states, which is 4 times uh, the weights of the model, it includes atom momentum, the atom variance, floating point 32-bit for these optimizer states, then we are looking anywhere between 4 to 5 times the size of these, which is like 14 into 4, which is 56 GB. And we are looking at the activations, the master weights, the overhead for calculation and everything. We need tens and more of GB here. Yeah, totally if you combine all this, it's 50, 60, 70, 80, 80 plus GB at least on a minimal. Okay, comfortably we are looking over 80 GB. Yeah, note what dominates here: the optimizer states here, this one, atom momentum variance, the floating point 32 numbers, and so on. Not the model is the lowest of the weight, because we are looking at floating point 16 of a 7 billion parameter, which comes to 16 GB. 17 into 2, that is the 14 billions. If you do the math, you'll get the GB part. We did this calculation in part 1. Go back and look at it. Yeah, Adam carries 2 extra numbers per trainable parameter, and that word trainable is the crack LoRa drives a wedge into. Okay, so what we are saying is, if there are 10 enterprise clients and each of them had a 14 GB checkpoint, we are anywhere between 140 to 150 storage costs, the serve, the version, and the rollback. All that adds a lot of complexity. So if we had 10 customers, this is 140 GB. Okay, just for the model weights and the checkpoint that we need to produce around that. Okay, and fine tuning was expensive to run and was expensive to own as well. Okay, now this adaptation that we are talking about says that, hey, when you adapt a pre-trained model to a new task, the change to the weights is delta w. Yeah, and it has low intrinsic rank. So what we are saying is, the model already knows the language. Adapting it to legal contracts or your support tone is a small structured nudge. It's not a rebuild. You don't have to rebuild the whole of the W, which is weights. You only need to add this delta W, which has low intrinsic rank. Yeah, if the update is low rank, don't spend full rank money learning it. So you don't have to spend all of the money, tens of 20s of GPUs to train all of these weights. That's what we are saying. Yeah. So what they are saying is, if you see the full fine tuning as w dash is equal to w plus delta w, which is the weights, then delta w is d by d, where d is the parameter size. Okay. What they are recommending is, in LoRA, which is low rank adaptation, we are saying this delta w can be represented by b dot a, where b is d by r, a is r by d. We already looked at this concept in users by item matrix, how we can bring a k as a parameter, where r is less than d. There we saw r as a, or k as a minimal of m and n, which is d and d here. So we are seeing r is less than d. So we get 2 dot d dot r parameters. Yeah, 2 into d into r. Now this is much less compared to this d square parameters, because r is less than d. Okay. So delta w is never found at full size during training. We don't have to. You learn its two factors directly, and their product is the update, which is d and r. Okay. The rank is the only known knob, and it's a product decision, not an implementation detail. Now imagine there is a W weights matrix that is 4096 by 4096, and you have to do a delta W, which will be also of the same size, because we are trying to add here W plus delta W. Okay, so delta W will be also be 4096 by 4096 matrix, and if we had to train all these parameters, it will become 4096 square, which is 16.8 million. Huge in number. Now LoRA, which is low rank adaptation, or low rank decomposition that it says, what we do is we split this delta W into b and a, d into r, r by d matrices, two matrices, where d is 4096, r is yet to be known, but it should always be less than 4096. Yeah. The base model weights w0 are frozen. We w dash, we don't change, they are still the same. Only b and a are trainable, so we train only these two matrices. Yeah. What does the savings looks like? If you're going to look at 4096 as a size, if we take r as 8 as a value, 2 into 4096 into 8, which is 65,000. 65,000 of 16.8 million is 0.39% of the full fine-tuned model. 256 times smaller than training the complete W, or the weights, or the fine-tuning of the whole original weights. Yeah, 256 times lesser or smaller. That dramatically lowers the cost of training. And this was the first question that we asked. If a CFO is saying from tens of GPU, we are saying one GPU for one afternoon, what has gone different? This is our answer. We have decomposed it into two matrices, and we are only training B and A matrix, and we are done. So the scaling factor is the question. So in practice, W dash will be W plus delta W. Delta W is alpha by R into BA, where alpha keeps the updates magnitude stable as you change R. Okay, it means fine tuning R does not force you to retune the entire learning rate. The initialization, A is random Gaussian and B is initialized to 0, so B dot A is equal to 0, and then as you start training, the weights keep differing. Yeah, and then you get to a good point where B dot A into alpha by R plus W gives you the actual W dash. Yeah, that's how we are looking at it. The zero initialization is quietly elegant. Yeah, there is no movement where the model is worse than the base because of random noise you inject. Worth pointing out on camera, yeah, when you show it to the CFO. Where the memory saving actually comes from, W is frozen, no gradients for it, no optimizer states for it, no update happens. Only A and B trains. Yeah, we just looked at it. And that 56 GB of Adam state collapses to a rounding error because the model size is considerably reduced now. Yeah, misreading, this is the single most common error in LoRa conversations, because people, when they project the multiplication values, they consider all of those values. We need to look at only the R value for B and A and calculate the size from there, 2 into D into R. So fine tuning LoRa and QLoRa. QLoRa is the quantized LoRa. We are going to look at it. So how does the model look like? When we are training in fine tune, we take all the 7 billion parameters and fine tune it. So 80 plus GB is what we looked at, whereas in LoRa 40 to 40 million is the size of training. Quantized LoRa also is the same, except that instead of floating point 16 we use 4-bit our 4-bit floating point multiplications. Okay, and the base weights are frozen. They do not do this, but here we are training them. Optimizer state is enormous, here negligible, here negligible, because there is hardly any calculation to be done here. Typical hardware, multi GPU clusters, single high-end GPU, a single consumer GPU itself would solve the problem here, because the number of parameters multiplication that we were looking at were hardly in 65k parameters. Artifact per task is 14 GB checkpoint, tens of MBs. This does not change here. Yeah. All weights are updated, billions of training, multi GPU, single GPU, consumer GPU. That's what we spoke about. Yeah, LoRa learns tiny patches B and A on top of a frozen model. Big impact, tiny cost. Yeah, that's why LoRa has become a default learning model, training model for fine tuning your frontier models or large models as well. So, how does the uh, parameter efficiency and memory efficiency change? Here we are saying that, hey, for the parameter efficiency, how few numbers we train and ship, because we have reduced the total number of parameters that we need to train by a huge factor, such that we get only 0.39%. In that case, storage costs are reduced, the versioning and distribution economics is reduced, only few tens of MBs per customer are required instead of tens of GBs. Memory efficiency, again, instead of GPU RAM, multiple GPU RAMs, we just need a single GPU. Yeah, that's all we need. Naming which one you mean makes you noticeably more incredible in the room. Ideally, as a product manager, we need to be taking both into consideration. We need to be looking at LoRa, maybe look at quantized LoRa as well, if the reduction in quality is not a big impact for us. We need to merge for speed or keep separate for scale. That's a decision we'll have to take. Yeah, because when you merge it, b dot a can be added into w after training. Okay, w plus ba is just a matrix of the same shape. Inference then adds zero latency, because we are just adding one addition there, w plus ba. Or we don't. Yeah, we keep adapters unmerged and hot swap them for per request. One shared base model sits in GPU memory, serving hundreds of per customer adapters. The second pattern that we could look at is multi-LoRa serving, as in virtual LLMs and SLoRa, standardized LoRas. It is the technical basis for per tenant customization economics. It is the difference between hosting one model and hosting one model per customer. So huge differentiation. This brings us to product manager perspective. While the mathematics is clear, we have understood what it takes, there are 4 decisions still with product manager, and one mistake here is something that we should always prevent. Lower R, it would mean that we are doing it cheaper, faster, smaller adapters. The risk, underfits a large distribution shift. So that's the challenge. Yeah, it's usually enough for tone, format, and schema adherence. Higher R would mean more capacity for genuinely new task structure. There is a lot of creativity, but it also overfits small data sets and costs more on every axis. Yeah. So the LoRa paper's tracking finding is that rank as low as 1 to 4 often suffices. We don't need beyond that. But you could always start low and raise R when evals say you must. So after every run that we execute for training these BA, which is LoRa values, B dot A, we need to run our evals and ensure that quality doesn't drop. Yeah. So what R did we use? What did R is equal to 16 by us over R is equal to 8 on the golden data set? So that's the eval. Did it improve? Did it deprove? What happened there? Yeah, that's a principal level question we need to ask. And it becomes from a kbex decision to an opex line item, because every time we run this, now we need to infer the values, and every time we have to infer, there is a lot of multiplications being done, a lot of compute being done, and we will have to predict the answers. So it becomes a opex line item, not just a training problem. So fine tuning stops being a one shot bet and becomes an iteration loop. Every time there is a change, upgrade happens, we need to do something like fine tuning. So what happens when we use full fine tuning, which is FT fine tuning versus LoRA? What do we train on? That becomes a question. And behavior versus fact, if you want to change the behaviors, fine tune the model. If you want to identify certain facts, we always have the RAG systems to be built. For example, you're trying to change the system's tone, format, schema adherence, task structure, domain vocabulary, refusal patterns. You need to fine tune or use LoRa. Okay, but if you're trying to teach the model certain facts, facts keep changing. For example, today the price of a particular chip or a system or a book or a car or a vehicle could be different. It could be maybe some x. Tomorrow it will change according to the economic conditions. It will become y. So facts keep changing. Retraining on every change of a fact is absurd. We can't do that. We don't know when it will change, so you can't keep training that. What would we rather do? Keep them as documents, create a RAG around that, and feed it into the LLM. Yeah. So both systems, so both of these are being used today by production systems. If it is facts, you use RAG. Behavior, you use this. So one base model, many adapters. That's how we are solving the problem here for multi-tenant SaaS economics. So three things that we need to keep a track of on our roadmap: pricing and packaging. Custom model tier becomes viable at software margins rather than at service margins. Yeah, we will cover this in track D in one of our upcoming sessions. Data governance, we can't put all the customers' data into training into one. That will be a huge compliance issue. So we need to be very careful about where we draw the boundary and whose data can be trained on what models. So fine tuning might not solve the problem. RAG could. So we look at a fine balance between those two. Versioning, the one that will surprise everything, because base model keep upgrading, invalidating the adapters. So we'll have to train those adapters against those specific weights of the frontier models or the main LLM model. So when we say we are upgrading the base model, means we are retraining every customer adapter as well. Yeah, budget for it from the beginning, not in the end. Okay, put the base upgrade tags in the plan before it appears in an incident review. Yeah, so maybe the model changes, the output changes, then we find it in a bug, then we try to upgrade the system. It's a cost, or it's a base upgrade tax. We should avoid it or plan it from the beginning itself. And here are six misconceptions that we should ideally look at. Eigen decomposition and SPD are basically the same thing. They are related but not interchangeable. Okay, eigen decomposition needs a square matrix. We looked at this. And singular value decomposition need not. It can be rectangular in nature. It works on all types of matrices. Yeah, they coincide for symmetric positive semi-definite matrices. Again, too many words. What it means is it works for square matrices, and if it is not, then we know that we have to use principal component analysis. Higher rank means a better matrix. Need not be. Ranks do not define the quality. Ranks only measure the information content. Higher rank matrix may just as well be noisy. So most of applied machine learning is to deliberately choose a lower rank. LoRa gives you a smaller model. No, it does not. The base model is always unchanged and the same size as well. LoRa gives you a small update to a full size model. Yeah, the savings are in training and in per task artifacts, not in inference footprint. Fine tuning teaches the model new knowledge. No, it does not. It only helps train the behaviors. It does not teach facts, because if facts were to be trained, it needs a lot of compute every few hours or every few days or every few weeks. It will go stale also very frequently, and that's why we do RAG. Okay, PCA is safe because we kept it 95% of the variance. Variance is not task relevance. Discarded low variance direction can be the one your classifier or retriever depended on to tell how unique it was. Okay, measure the downstream metric, not the variance ratio. Low rank approximation always saves storage. Keep only k of m plus n plus 1 less than mn or m or n of values, because past the break even k you are storing more, not less. We looked at the quality versus storage graph, where beyond a certain percentage of storage, the quality does not improve. Yeah, and uh, you're paying more money to just store all those unnecessarily. This brings us to the last section, which is the interview prep. We have 6 questions that we could look at or more. Uh, while we looked at a lot of mathematical uh, compute, this does not mean that we are attending engineering interviews. What we are helping decide is what's the quality, what's the accuracy, how much latency are we looking at, and the total cost of product that we are building, not just as capex but opex also. So typically you might be asked like, hey, what is matrix rank and why should a PM care? Yeah, matrix, we understood that matrix rank, we understood that is the number of genuinely independent directions in a matrix. If there is a lot of noise, there is dependent redundancy and duplicacy, it does not really help. So we need to lower them using compression, dimensionality reduction, or LoRA. And if a matrix is effectively low rank, you can store and compute far less of it with almost no quality loss. Yeah, the question that we are trying to answer is, what is the effective rank of our data, by saying how much are we overpaying, because after reducing it we have a lot of lower storage costs, lower compute costs. Explain singular value decomposition to a non-technical stakeholder. Yeah, any table of numbers can be broken into a list of underlying patterns, sorted from most to least important. We looked at this. SVD does that sorting. Yeah, once things are sorted by importance, you can keep the top few and discard the rest. This is how image compression, system recommendations, or recommendation systems, and efficient fine tuning, all of them work. What's the difference between eigen decomposition and singular value decomposition? Eigen decomposition, we looked at, needs a square matrix and doesn't always exist. Singular value decomposition works on any matrix type and always exists. Both say rotate, stretch, and rotate, but SVD is the general numerically stable version, which is why applied work reaches for it. Okay, for symmetric matrices, they coincide, which is why PCA can be explained either way. How does LoRa make fine tuning cheaper mechanically? Instead of training a full D by D weight update, LoRa will do or create two skinny matrices, D by R and R by D, and adds their product with lower sizes. We saw that with 4096 dimensionality matrix and R is equal to 8, that was a 65,000 parameter calculation or fine tuning being done instead of 16.8 million, which was 256 times cheaper or smaller. The base weights stayed frozen, and we didn't have to carry all the gradients or optimizer states for them. And the optimizer state is what dominates the training memory. As an example, we looked at 7 billion 16 floating point model that needed 56 GB of optimizer state management. Now with this lower 65,000 parameters, we don't need that much size. When would we use LoRa fine tuning versus RAG? LoRa is typically used for behavior change like tone, format, schema adherence, task structure, domain vocabulary. RAG is used for facts, anything that changes that needs citation or reference and is customer specific. Yeah, fine tuning of facts is expensive because it goes stale immediately. Most real systems use both. LoRa is how it talks versus RAG is what it knows. So I would either choose an evaluate set and not an intuition. That's how we will build it, and that would be the most optimal model. Your engineer wants to increase LoRa rank from 8 to 64. How do you respond? I would ask what problem is it solving. Higher rank buys capacity for a larger domain shift at the cost of more parameters, more memory, larger adapters, and more overfitting risk on a small data set. So we need to have a golden data set that says r is equal to 8. At r is equal to 8, is it underfitting, overfitting, or on which slice of the data? Can we run 8, 16 and 32 in parallel and compare? Yeah, because comparison will give us the right r value. Since LoRa is cheap, the answer should be measured rather than argued. Last set of questions. We are upgrading our base model. What happens to our customer fine tunes? Adapters are trained against specific base weights, so they don't transfer. Every customer adapter is retrained separately and revalidating against the new base. That's a real migration cost, and it belongs to the upgrade plan, retraining compute, rerunning evals per customer, and a rollback path if a customer's quality regresses or falls below a certain threshold. Last question: what's the risk in reducing embedding dimensions to cut vector database costs? While we are discarding directions, the discarded ones don't guarantee to be relevant to our task. PCA optimizes for variance, not for retrieval quality. So if we were to treat it as an experiment, we need to cut dimensions, then measure the total recall, and downstream answer quality against a golden set. I would also compare against Matryoshka embeddings, which are trained to degrade gracefully under truncations. So if you had 1536 embeddings, what it typically does is it reduces it to 512, then 256, and then so on. It gradually or gracefully reduces the size. And to recap what we learned today, we learned that there was one idea that we said, hey, how do we identify which are the most important vectors or dimensions in my database, sorry, in my matrix vector, in my matrix or vectors, and how do I reduce it to reduce the cost and so on, and how do I fine tune or ensure my system stays up to date, captures the facts without degrading and without me incurring a lot of cost. So we looked at rank, which named that gap. Linear transformations, we looked at how certain transformations become irreversible. We looked at eigen, what are the natural axes and why they do not, and how them not being changed, they get to be called eigen. SVD, singular value decomposition, we looked at how we can form a matrix and sort by importance. Low rank approximation, we looked at why this is the best way to exploit the gap. PCA, we looked at it same but only centered around the mean. The matrix factorization, we said, hey, what if ratings were sparse data, and how would you apply PCA to matrix factorization? Or singular value decomposition to users are movie ratings table. Sparse versus dense, we looked at how two philosophies on how storage happens, where they prove to be beneficial one over the other, and how in 2026 we are looking at a combination of both. Then we looked at low rank adapters adaptation. In this we said, hey, same move that we have applied across, but it can be applied to a weight update. It's just that 256 times smaller, cheaper in compute and storage compared to what was existing earlier. Yeah. So that's all about the track A part 2. uh, we will meet in track B part 1 tomorrow. Thank you.